Mr. Hant is going to move the Skype box out of the way so that you can see what's behind it. And then hopefully when Thomas goes out and comes back in, he's able to hear this time. All right, so looking at those graphs now, what I would like you to try this time now is which of those three graphs has an increasing rate of change? And what that would mean is those steps we were talking about, those steps should be getting steeper. So which of those three graphs, 1, 2, 3, or 4, has an increasing rate of change? Okay, and I'm going to try and draw stairs for you on these ones. Okay, we're going to, Mr. Andy's going to go get a pen. We're having trouble drawing straight lines on this. We're looking for, I believe I said an increasing rate of change. I forgot what I said. I'm going to type it here so I can remember. Increasing rate of change. All right, increasing rate of change means take a look at these graphs here and imagine going over and up, over that same amount and up, over and up, over and up, over and up. Which one of these would have the stair height getting larger? Because that's what an increasing rate of change is. Which one of those has the steps getting larger? Okay, so that's not guess two. Two is a weird case that I'll talk about. The case we haven't covered is definitely not 2. So he's got a pen now. He's going to try and draw with a pen rather than the mouse.
Guyamachiel, Thomas 127.
Is now joining.
Till, Aidon 728.
Mr. Hand is going to see
Is now joining.
Rate triangles on the first one for you. So can you see how he's trying to draw those rate triangles? And you see how the height is getting larger. The height of each step is increasing. That one was the increasing rate of change. All right, now see if you can find the one that has a decreasing rate of change. And now in a decreasing rate of change, if we were to draw that little staircase, the heights of the steps should be getting smaller. So again, don't guess two. We'll talk about it at the end. Which one of the 2 remaining has the decreasing rate of change? Okay, just a couple more seconds to see if anyone else wants to type and see what it is. Mr. Hant is going to try and draw those rate triangles now. All right, so 3 is the correct one. Try and illustrate that for you. So you can see how the height of those stairs is decreasing. Oh, that's really hard to draw on that. I would not be doing any better trying to draw there. So which of the 2 remaining now, 2 or 4, has a constant rate of change? So we know 3 was the decreasing rate of change. Which one has a constant rate of change? Now we just have 2 and 4. Okay, just wait a couple more seconds. People are still typing there. Yeah, and the correct one would be the last one. The rate of change on that last one. In fact, would the flag be moving in the last one? Because each of these were representing a flag going up the flagpole. Is the height of the flag changing? Or is it stuck at a value? So if you can just type what you think there. Is the flag actually going up the flagpole, or is it stuck at a certain height? Great. You guys are right. It's stuck. So it's the rate of change is 0 there. It's not moving up the flagpole. Now, what do you think the second one is saying? That's a weird one there, eh? So on the one on the far right here, what we can see is time is running, time is changing, but we're not actually moving up or down. So the height is stuck. Time changes. What's not changing in this one in 2? So I'm going to repeat again. In 4, the height doesn't change, but time does. What isn't changing in the middle one there, number 2? If you can just type something for me. What's not changing there? Excellent. So you guys have got it down. Time isn't changing. So it turns out this graph here is absolutely impossible to do. You cannot move a flag up a flagpole in absolutely no time. In fact, what we have going on here is that this single instant of time, this flag is in many different places on the flagpole. And of course, that's impossible. So graph number 2 is completely impossible to do. All right, so now we're just going to take a look at the slide below this. I just want to do a quick review before we just start today's work. So we'll wait for that to load up. It had a picture on it. I'm not sure why. It's there earlier. Maybe we're just going to try a refresh. The wonders of technology. There we go. All right, so this is what we were looking at yesterday. Notice how all of these are curving up. They all have positive. Actually, I should ask you, what kind of correlation do those have? I should not be telling you because that was from the last unit. What kind of correlation do those 3 graphs have? I'm going to wait for you to type something in the chat box. Based on your knowledge from last unit, what kind of correlation? I'm waiting for you guys to type something. I don't want to give you all the answers. So what kind of correlation does each graph have? As the independent variable increases, the dependent variable is increasing. What kind of correlation is that? Excellent. It is indeed positive correlation. Let's do some more review from last unit. Which one is the independent variable? Which one is the independent variable? Let's give you some time to type. Which one's independent? Perfect. So the one on the horizontal axis is time. Time's independent. Height is dependent. All right, now I'm going to give you a challenge question. Is this relationship an example of continuous or discrete data? Continuous or discrete data. See if you can remember what the difference is between those two terms. Continuous or discrete. And if you've forgotten the difference between them, continuous is something that you would measure and you could have decimals. It would make sense for there to be decimals. Discrete is something that you would count. So do you think you're counting the height or are you measuring the height? With regard to time, do you count time or is time something that's measured? Can you have half seconds, quarter seconds, third seconds? So think of it, let's start with height. Do you measure height or do you count height? Yeah, so height is something you measure. Now to give you an example of what I mean, if you were 1 foot tall, you don't suddenly quantum leap to 2 feet in height a year later. you hit all the values between. It's a steady, continuous growth from 1 to 2 feet. You hit all the values in between. That's what it means to be continuous. Discrete would be you're going to jump from one value to the next, making sort of a quantum leap. Now think about time. Is time measured or is time counted? Can you have decimal values for time? Does time jump from 1 minute to 2 minutes without hitting anything in between? Or do you hit all the values between 1 and 2 minutes? I'm going to give you a couple more seconds because some people are still typing. Yeah, so time is measured and height is measured. Therefore, this is, I'm going to type it here, so I'm not sure you know how to spell it, is continuous. So this is an example of a continuous relationship. It's not discrete. All right, so we had the decreasing rate of change is the red one. The constant rate of change is the blue one. And the increasing rate of change is the green one. And the constant rate of change will be easy to tell because it will be the line and the other two will be curved. I like to say this red curve is becoming more horizontal. Remember, this is a horizontal line right here. This one's the vertical. And this curve is getting steeper or more vertical. If it gets more vertical, it is your increasing rate of change. So what we're going to do today now is we're going to change the scenario. Instead of filling vases, that's what we did yesterday. Today we're going to burn candles. Did you have the GSP sketch? Perfect. So Mr. Hans is going to open the GSP sketch. And then we'll give time for that to show up for you. And then we're going to start with the first candle when it loads up. All right, I'm presuming that you can see that there, right? Excellent. So we're going to start with that pink candle. And so if we remember from yesterday, we ended up getting curves when the width of the vase was not constant. If the width of the vase was constant, we got our lines. And when the width of the vase was increasing, the rate slowed because it took less height could be filled in each time interval. When the vase narrowed, in a time interval, greater height would be filled. And that gave us an increasing rate of change. So what kind of rate of change do you think you're going to get for this particular candle? Is it going to be a constant rate of change? Is it going to be an increasing rate of change? Is it going to be a decreasing rate of change? So remember, we're talking about the rate of change here. So with regard to a rate of change, if something has a constant width, the rate of change will be constant. If its width is increasing, you'll get a decreasing rate of change. If its width is decreasing, you'll get an increasing rate of change. So first thing I want you to take a look at that candle. What kind of width does it have? Let's answer that question first. Is the width constant? Is the candle increasing in width or is it decreasing in width? What's happening with regard to that candle? Okay, excellent. So you've got that the width is constant. So if the width is constant, then the rate of change will be constant. So this is going to have a constant rate of change. Now, obviously we don't have whiteboards in front of us, so I want you to be drawing this on paper. What do you think this is going to look like? If it's a constant rate of change, what do you draw? Maybe you can tell me what it is you're visualizing. What are you visualizing that this graph will look like? Okay, now you can type something for me so I can see what you're thinking. I haven't learned to read minds yet. And are you going to be drawing a line or a curve? Is that what you were imagining? A line or a curve? Okay, so we're going to run this now and see if you're right. So most people are expecting this to be a line. Let's start it up. And is that how you envisioned it was going to look? Or did you think it might have positive correlation? Because you were thinking about the case from yesterday. And usually when I do this in class, very few students draw this correct. Everyone draws a line, but most students draw the line from yesterday's work, which has positive correlation. So yesterday we were starting here at the origin, and then the line was coming up this way. Positive correlation because the height was increasing. But because this is a candle then, and we're burning it, then its height should be decreasing over time. Does that make sense to everyone why this has negative correlation? Perfect. So we would say that this relationship here has a constant rate of change because it's a line, and it has negative correlation because it's coming down. All right, what we're going to do now is show the next candle. And some guiding questions for you. What's happening to the width of that candle? Is the width of that candle increasing, or is the width of that candle decreasing? And remember, when the width decreases, you get an increasing rate of change, i.e., the curve is going to get more vertical. If the width was increasing, you would get a decreasing rate of change, which means the curve would get more horizontal. So has everyone decided, is the width of that candle decreasing or increasing? So everyone quickly type something. Is the width increasing or decreasing? Yeah, remember that a candle burns from the top down. So you can't look from the bottom up. You got to look from the top of the candle down. Again, I'm going to repeat because this is a candle and it's burning. It starts burning from the top. So you have to start here and come down this way. That's how a candle burns. It doesn't burn from the bottom up. All right, so can we rethink our positions now? Because the candle burns from the top down. Perfect. So the width of that candle is decreasing because we're looking at from the top down. Now, if it is decreasing, the rate of change will be increasing. Let's see if I can get a marker out here and just kind of draw some marks. Remember, we were having these little trapezoids, right? Maybe you try that with your pen. And the heights are going to increase as we go down because each one of those trapezoids has to have the same area. And if we make A and B smaller, then the distance between, or the height for each trapezoid has to end up getting larger. So we're trying to draw those with larger height segments. So that's going to create an increasing rate of change. In an increasing rate of change, the curve needs to get more vertical. But remember, they have to have negative correlation. So maybe if you have a paper beside you, could you draw what you think that's going to look like? A negative correlation getting steeper. And then I'm going to just give you a few seconds to think about what would that look like. Negative correlation getting steeper. And then we're going to show you what it would look like. All right, so we're going to play this out now for you. Start it up. The brown curve needs to be above the pink, and I guess we didn't actually watch the simulation, but you see how the brown candle is taller than the pink one? So it's curved, it's concave down, and it is above the pink curve. And now that curve is becoming more vertical. And then we'll run one more time through this and we'll show you the tangents. Now, when we show you the tangents, because this is an increasing rate of change, what should happen to the slopes of the tangents? Should the slopes of the tangents get steeper or should the slopes of the tangents get less steep? Thinking about that brown curve that you just saw there, because we're going to show you the tangents in a minute. And we'll just highlight that so that they can watch it. We're not going to start the simulation yet. We would like to know if the slope of that tangent line will increase or will the slope of that tangent line decrease. I'm just going to type that question here. We're looking at the slope of tangent line. Will the slope of the tangent line increase or decrease? And remember, this is an increasing rate of change. Okay, perfect. So we're going to start this up. If the height values start increasing, the change in height values over time, if the change in height values are increasing, that tangent line needs to get steeper. And now we can see that visually happening here. That tangent line is definitely getting steeper. And now we can see, of course, look at that brown candle is taller than the pink candle. But it will catch up to it eventually because it's accelerating, because that tangent line is getting steeper. And the rate now is exceeding the pink rate because I can see that line is a bit steeper now. And then eventually it will catch up. Definitely we can see the greater steepness now. And then those candles will extinguish at the same point in time because brown was accelerating. All right, reset. Now we're going to look at the last candle. All right, what's this candle doing? Its width. Is its width increasing over time or is its width decreasing over time? Remember, you got to look at the top of the candle down toward the bottom. What's the width doing? So what kind of rate of change will we get now? I'm going to just type rate of change next, so I'm distinguishing between the two. Rate of change. You are correct. The width of that candle is increasing. What will happen to the rate of change then? What kind of rate of change will you get? Anybody else want to type something? What kind of rate of change are we going to get? Remember, there was an opposite play going there. When the width of the candle decreased, we got an increasing rate of change. So if the width of the candle increases, we should get a decreasing rate of change. Now, what do you think that's going to look like? So can you visualize what that's going to look like? So have you made a guess at what you think that curve is going to look like? And then we're going to show you now. No, we'll show the point now. I'll just run through it. All right, so there's the curve, and notice how we have negative correlation because the height is decreasing, and that curve is becoming more horizontal because we have a decreasing rate of change. And we would call this curve being concave up now. So a decreasing curve that's concave up. And then we'll just let that finish out. And then what we're going to do next is we're going to go to the tangents. So we're looking at the purple candle, slopes of the tangents. So I'm just put a little note there. That's what we're looking at now. The purple candle, slopes of the tangents. Mr. Hant is going to show the tangent now. We're not going to play it yet. What's going to happen to the slopes of those tangents there, given that we think this is a decreasing rate of change? And we're going to give you some time to do some typing. It's a decreasing rate of change. What should happen to the slopes of those tangents? Okay, again, I'll repeat. It's a decreasing rate of change. which means the curve is becoming more horizontal. So the tangent line itself should become more horizontal. So look where that tangent line slope is right now. Look where it is. If it needs to become more horizontal, because that's what a decreasing rate of change does, what will happen to that tangent? Will it get more or less steep? Again, I'm looking for some feedback for you. More or less steep? What will the tangent line do? All right, so let's watch this now. The only way to get more horizontal, you are correct, is to become less steep. And look at it, it's getting less steep now. And notice how purple was way in front. The only way for brown and pink to catch up would be for purple to be decelerating. That rate of change has to be slowing. If the rate of change isn't slowing, then the heights from the other candles will never be able to catch up to it. All right, so what we're going to try now is still working with these same three candles is in terms of change, how the height is changing, which color candle has its height changing at a constant rate? Which candle has its change in height changing at a constant rate? Just tell me the color there. Which, again, repeat one more time. Which candle has its change in height changing at a constant rate? Or has its height changing at a constant rate? Perfect. It was the pink one. All right. Now, which candle has its height changing at an increasing rate? So again, repeat. Which color candle has its height changing at an increasing rate? So we're going to have the height changing, but it's changing at an increasing rate, which means the curve would be getting steeper. Okay, so let's reset that again just so we can look at them all. All right, we just want to make sure everyone's clear on what's happening here. If the rate is an increasing rate, the curve has to be getting steeper or more vertical. The blue, it's actually a purple curve, but it might look blue on your screens depending on how your color is set up. That candle is not changing at an increasing rate. Can you see how that's becoming more horizontal? If we show the tangent line again and just drag time around there, it'll go faster. All right, see how that tangent line is becoming more horizontal? As Mr. Hunter drags that around the clock, that tangent line is starting to approach the horizontal axis because that's a decreasing rate of change. Let's do that, hide that tangent and show the brown tangent. Okay, now again, he's going to drag time around and notice how the brown tangent line is becoming more vertical, i.e. it is becoming parallel or closer to being parallel to the height axis. Can everyone see that? All right, so now which candle's height is changing at a decreasing rate? The color of the candle whose height is changing at a decreasing rate. Which one of those three candles? I'm waiting for you guys to type something in now. For which of those three candles is the height changing at a decreasing rate? Anybody else want to type something in? We're looking for the candle whose heights are changing at a decreasing rate. Yeah, okay, purple is the correct answer. Now we've got one candle left. All right, there's our last candle. What do you think its height over time is going to look like? Feel free to type anything you want in the chat box. No such thing as a wrong answer. Every hypothesis is a good hypothesis. If scientists were afraid of being wrong, we would never have discovered anything about the world. What do you think is going to happen with this orange candle here? What's special about the orange candle? Any observations? Okay, so Heidi's made a good observation. She says the candle's not going to, it's not lit. So what's going to stay the same? So what do we think will stay the same? So remember, we're measuring height and we're measuring time. Does time stay the same? Or does the height stay the same? So remember, in this simulation, we are going to turn the timer on. So time will have to move. So what isn't going to change? What won't change? That's the question I'm asking you now. What won't change? Remember in the simulation when Mr. Hanta hits start, that clock is going to move. All right, so let's watch the simulation. So he's going to start the clock. Time is moving, but the height is stuck at 60. See how that candle, the height of that candle isn't changing. So we end up getting a horizontal line there. We do get a graph, very similar to with the vase, where when the water wasn't turned on, you thought there would be no graph, but there was a graph showing that the height didn't change. The height was stuck at 0, so we ended up tracing out the horizontal axis. Here, the height is stuck at 60, so we're getting our horizontal line coming across at 60, showing that our rate of change would be 0 centimeters per hour. Are we comfortable with why we got a horizontal line in that case? Okay, perfect. So now we're going to look at a summary. All right, so let's wait for this next slide to come out. This is your big key ideas across these 2 days. Every single relationship or function that you will study in mathematics is comprised of these 6 pieces. The left column is showing the ways you can have positive correlation. That little bit there. Positive correlation. The top one, can you tell me what kind of rate of change that just that top one has? Can you just highlight that first? That one right there. What kind of rate of change does that one have? Definitely has positive correlation. Can someone type in what kind of rate of change is that? Okay, perfect. It's a constant rate of change. So Mr. Hansen's going to click move. And then you'll see that the Pharaoh was moving at a constant speed. And the direction was in the positive direction. In this case, that was up. All right, let's look at the one below that. All right, what kind of rate of change will that one have? We can see it's positive correlation. What kind of rate of change? So again, we're looking at that second one down. Remember, for a constant rate of change, it has to be a line. This isn't a line, it's a curve. Okay, so it is an increasing rate of change because the tangent lines will get steeper. What does an increasing rate of change mean? Does that mean acceleration or does it mean deceleration? Increasing rate of change, acceleration or deceleration? Anybody else want to type something in? Okay, so correct, it's acceleration. Now watch when Mr. Hanta gets the Pharaoh to move. Watch how speed increases. Reset, we'll try that one more time. Starting out at a slow rate and then accelerating. I think, not sure if I have this online. There's a lag here, so you don't see it's not very smooth motion, but if you could see the computer that I am looking at, we can see the acceleration. I'm looking on my computer and it's hard to see because of lag. but that was accelerating. All right, let's look at the one below that now. Again, positive correlation, so the ferrule should end up moving up. What kind of rate of change is this? Think about the tangents. What are the tangents doing? The tangents get less steep. It's a decreasing rate of change. Yeah, that is a decreasing rate of change. So when Mr. Hanta hits move, the ferrule will be moving the greatest speed when it starts, and then it will be slowing to a stop. Try that one more time. Yeah, it's really bad on the lag here, so you can't see that. But if you could see the laptop I'm looking at, it would be deceleration. That's hard to see here, but I think we've uploaded this, and you can try this on your computer at home. You would see deceleration happening here. So this is a decreasing rate of change, and the ferrule is decelerating here. Moving up because the graph had positive correlation. So what's going to happen now is Mr. Hanta is going to highlight this one over here. You can see that one's been highlighted. So this is what I want you to talk about. What is the direction of travel now? Is the ferrule going to move up or is the ferrule going to move down? And then you have to tell us how the ferrule will move. At a constant rate, is it going to be an increasing rate or is it going to be a decreasing rate? And you could tell me constant rate, acceleration, and deceleration. So again, two things we want you to convey to us. The direction of travel, is the ferrule moving up or down? And then how will the ferrule be moving at a constant rate, accelerating, or decelerating? Okay, definitely. We got a couple of responses here. You've got the direction of travel correct, but now how will the ferrule be traveling? And remember, to decide how the ferrule is traveling, you have to look at the curve. If it's a line, it's a constant rate of change. If it's curved, then it's either curved to get steeper or it's curved to get less steep. If it's getting more vertical, it's acceleration. If it's getting less vertical and horizontal, it's deceleration. All right, so definitely going to move down now, but how? At a constant rate? Will there be acceleration or will there be deceleration? All right, constant rate is correct. Let's do the one below it now. Again, direction of travel. And once you've decided the direction of travel comes solely from correlation. What is the correlation of the curve? And then you have to look at the shape of the curve to decide the kind of rate of change. So again, we're looking at the one in the dead center. What's that one doing? Direction of travel. We're waiting for you to start typing. And then tell us on the kind of rate of change. Are you going to see acceleration, deceleration, or constant? Okay, now take a look at that curve. The curve coming down doesn't tell you anything about the rate of change. It's the shape of that curve. Is that curve getting more vertical or less vertical? If it's getting more vertical, it's an increasing rate of change. So again, you got to focus on two things. The curve coming down tells you direction of travel. It tells you nothing about the rate of change. To decide the rate of change, you have to look at the shape of that curve. And this curve is definitely getting more vertical. Would you agree? The curve is getting more vertical? Therefore, it's going to accelerate. All right, we've got it now. It's going to move down and it will accelerate. All right, let's see if we can put it all together on the last one, on the bottom there. Again, correlation will give you the direction of travel, be it up or down. Then you have to look at the shape of the graph to decide whether that's acceleration, deceleration, or a constant rate. I'll repeat again. A constant rate is a line. And remember, a line you draw with a ruler or a straight edge. If it's not a line, it will be curved. And the curve does one of two things. It either gets steeper and more vertical, or it gets less steep and more horizontal. Less steep is deceleration, more steep is acceleration. Can you quickly summarize what's happening on that curve? All right, so Thomas has got the right answer there. It's going to move down and it will decelerate. One left on the far right there. Top column, far right. What's going to happen there? Direction of travel and rate of change. And again, direction of travel and rate of change. So we'll take a look at correlation. The correlation is not positive, it's not negative. We have a horizontal line there. So that's going to indicate no movement, right? So the guy's not moving because we don't have positive or negative correlation. So the Pharaoh is going to stay put. Now, why we got a graph tracing out is because distance isn't changing, but what is changing? Someone want to type in for us, what is changing? That's how we got a graph, because something was changing. You're right, the Pharaoh is not moving, stays put, but something is changing. That's how come the graph was changed or traced out. What is changing? Anybody have any ideas what changes? Nobody has any ideas? So what was the independent variable in our scenarios? Distance was one, and the other variable was? We had a little clock there. The clock measures. Can somebody type it for me? Very good. Heidi's got it. Time. So time is changing on the far right. Distance didn't. That's why we got the horizontal line. So in grade 9, what we do now, Mr. Hant is just going to highlight the top row. Grade 9 is all about the constant rate of change. We're going to move balance of this unit and the next unit is going to be all
Dalton
about
096
Is now exiting.
all about the line. The other curves on the bottom, you're going to look at in grade 10 and grade 11. All right, now we're going to move to some scenarios and applications. All right, there's the car there. You're going to tell us something about the direction of travel. This is scenario 1. In what direction will that car be moving? It's either forwards or backwards. And then will the car be accelerating, decelerating, or moving at a constant rate? So we're looking at the blue car right now. So I'm just going to type in blue car. And then we want you to type direction of travel. And you could just say forward or backwards based on the correlation of that curve. And then you can type ACC if you think it's accelerating, DEC if you think it's decelerating, and then maybe you can put CON if you think it's constant. Also direction of travel. You got to do both. Some of you are giving me the correct type of rate of change, but I need to know direction of travel as well. All right, so perfect. So forward and acceleration, maybe we'll just see if that shows up. Mr. Hant is going to start that car. And well, we definitely could see them moving forward. It was harder to see Now, was it accelerating? So let's try this again. He's going to start that car up. The tangent line is showing. What's the tangent line doing? Is that tangent line getting more or less steep? So take a look at that tangent line. Is it possible to highlight the tangent line? Okay, so we've got the tangent line highlighted now. We're going to start it up. Is that tangent line getting more steep or less steep? So look at the steepness initially. I can see it dropping. That's getting less steep. If that were a hill, that hill now is much easier to climb than the hill we had at the beginning, right? We're going to play that one more time. Look at that pink line that we've got highlighted now. It's highlighted in pink. Initially, that's very steep, and then it's shallow. It's an easier hill to climb in the end. So those tangents are getting less steep. Can everyone see that now? Can you please type confirmation? Because you're giving the wrong answer. The tangent lines are getting less steep. Can everyone see that now? All right, so less steep tangent line means deceleration. So this car is moving forward, you got that correct, but it is decelerating. Are we comfortable with that now so we can move on to another car? This car moving forward but decelerating. We okay with that? Okay, perfect. Let's try another car now. We're going to hide that. We're going to show car 2. All right, there's car 2. So direction of travel and how will it move? And hopefully we're getting the idea that if it's curved, those are either accelerations or decelerations depending upon whether the curve gets steeper or less steep. Is this a curve or is this a line? All right, so now tell me how this car is going to move. What's the direction of travel and what is the rate of change? Will it accelerate, decelerate, or constant rate? And also add the direction of travel. Anybody else want to type something? I see 2 responses so far. Those responses are indeed correct. All right, so we'll just watch this. Well, certainly we'll get the direction of travel out of this. I'm not sure you can tell it's constant. So that car moved at a constant rate and forward. All right, we're going to hide car 2. We're going to go for car 3 now. All right, so what's car 3 going to be doing? Direction of travel. You determine that by looking at the correlation. And then type of rate of change, you're going to have to look at the shape of the curve. How is that curve shaped? Is it getting steeper? In which case it's acceleration. Is it getting less steep? In which case it's deceleration. If it's a line, it's a constant rate. All right, so let's see what you're thinking. Forward and acceleration. All right, forward and acceleration is correct. The rate of change, we're not getting less steep, so I'm going to play that so that you can see. Watch the tangent line. See how that tangent line is getting steeper? Just want confirmation on that because some of you thought it was getting less steep. Look at that tangent line, definitely getting more steep. We comfortable with that now? Maybe you can just type in the chat box just to let me know. Okay, perfect. Reset. I'm going to hide that car. And now let's show car 4 now that we're getting the hang of that. All right, direction of travel and acceleration, deceleration, or constant rate. And again, direction of travel comes from correlation. And you have to look at the shape of the graph to decide whether it's accelerating, decelerating, or moving at a constant rate. What are we thinking for the green car now? I'll wait for you to type something.
Till, Aegon 728.
Is now exiting.
So direction of travel and rate of change both. Heidi, what do you think about direction of travel? Forward or backward? And I'm not sure if Emma, Gonzalo, and Liam are still here, but if you are, feel free to type something. Definitely going backward. You got that right. Now, how about the rate of change? Is it going to be accelerating, decelerating, or moving at a constant rate? Okay, Samuel, you got more steep. What does more steep now mean? Accelerate, decelerate. What's more steep mean? So if something is getting steeper, that means you're going to be moving faster. So it should be acceleration. The curve is coming down. I think you're confusing two concepts. The curve coming down, the fact that this curve here drops, that curve is dropping, that tells me the direction of travel. That's how I knew the car was going to go backwards. Now, how do I know what the rate of change is? I'm going to be thinking about that tangent line. Start it up. Do you see how the tangent line got steeper? Can everyone see that? That tangent line is getting steeper. The tangent line is getting steeper, so that means the car is accelerating. Everyone comfortable with that? Confirmation, please, because we had that backwards. I think you were mistakenly looking at the correlation. The correlation doesn't help you decide the rate of change. You have to look at the shape of the graph. We're good with that now? Shape of the graph to decide whether you're accelerating or decelerating. All right, we're going to hide the green car. I'm going to show that silver car. All right, tell me what's going on with that silver car.
Goncalo 161.
Is now exiting.
Silver car, what's happening? Direction of travel, rate of change. Okay, now for the rate of change, that doesn't look like a curve to me. That looks like a line. So if you're a line, it's not acceleration or deceleration. Great. Constant rate of change. Just start that up just to confirm that car traveled backwards at a constant rate. All right, on to the pink car. All right, what's going to happen for the pink car? Again, the correlation tells you direction of travel. You must look at the shape of the graph to decide whether it's acceleration or deceleration or a constant rate. If you've got a curve, it's acceleration or deceleration. If the curve gets less steep, you're decelerating. If the curve gets steeper, then you're accelerating. What's happening here for the pink car? Anybody else want to type something in there? All right, so you are correct. This one is backwards and it's decelerating. We'll just start this one up. There we go. So let's try that one more time. See what you can see on yours. It's very, very jumpy due to the lagging. But if you were watching it on Mr. Hansen's laptop, you could definitely see the deceleration. All right, let's take a look at the last car now. What's going to happen here? What's going to happen off with the brown car now? So let's take a look at the graph there. We are getting this horizontal line. Is the distance changing? That's the question I'm going to ask you. Does distance change? Is the car actually going to be moving here? Or is the distance stuck somewhere? What's the distance stuck at? Because it actually is stuck. What number is the distance stuck at? Yeah, it's stuck at 8 kilometers. So when Mr. Hanta hits start now, see the point swinging across there? Let's watch that again. The point swinging across is just showing you for all time units, that car is stuck at 8 kilometers. So the second coordinate for every point there, I'm not sure how well you can see that, is stuck at 8. All right, that reviewed the 8 curves. Now we're going to come to the next slide. Here is scenario 1. We're going to wait for it to pop up for you. So you need to decide this. Which car, let's do the first question. You see how there's red, there is yellow, and there is blue. Which of those cars will be accelerating? Look at the shape of the curve. If a curve is getting more vertical, that would be acceleration. Is there more than one car that's accelerating? I agree. Blue is definitely getting steeper. That curve is getting steeper. Is there another curve that's getting steeper? Yeah, you're right. Both blue and red are getting steeper. So those are the cars that would be accelerating. Is there a car that's decelerating? Thinking about deceleration now. Are any of those 3 cars decelerating? And remember, for deceleration, you need a curve, and the curve has to be getting less steep. So we've established that red and blue are getting steeper. Yeah, there are no curves that are getting less steep. So none of those 3 cars will be decelerating. Which of those 3 cars will be moving at a constant rate? Which of the 3 cars are moving at a constant rate? Anybody else want to type? Which of the 3 cars moving at a constant rate? Perfect. Now, which car is going forward and which cars are going in reverse? All right. Which cars are going in forward and which are going in reverse? Okay, so let's watch this and see. All 3 of the cars are going forward. How would I know that? Can you see that all of those curves have positive correlation. Does everyone see that? Can you confirm that? They're all going upwards. So the cars have, those curves have positive correlation. That meant they were all going forward. Everyone comfortable with that? Because some of you didn't know that they were all going forward. All right, so now we'll try scenario 2. We'll hide scenario 1. Okay, now let's be careful here. Correlation tells you the direction of travel, and the shape of the curve tells you whether you'd be accelerating or decelerating. So for acceleration, you'd be looking for a curve that is getting steeper. So we have silver, we have green, and we have pink. Do any of those curves look like they're getting steeper? You know, remember what steeper means. It doesn't mean going up. Going up doesn't mean steeper. It means the tangent lines. It has to get more vertical. So let's take a look at this axis over here. That's a vertical axis. Look like this is becoming more vertical. This is the horizontal over here. Does this curve look like it's getting more vertical, horizontal? Again, so let's take a look at this curve. As I move along the curve, to me, it's flattening out. Do you not see that? It's flattening out. Okay, let's focus on this curve right now. Can everyone see that as we move to the right, this curve is getting flatter? Very steep in the beginning. I wouldn't want to climb that hill at the beginning, but the further we move along this curve, I guess, the further we move along the curve, the less steep it is getting. Can everyone see that? The further along on that curve, the less steep it gets. Yeah, so that means the curve is getting less steep. Let's carefully analyze the pink curve now. Look at where it is in the beginning and look what it's doing toward the end. Is that getting less steep or more steep? Where does it look most vertical? At the beginning? Is that closer to the end? So take a look at the very beginning of this curve here. Do you see at the beginning how it's very close to vertical? And then as we move to the right, it's getting less and less steep. It's actually getting less steep. Can we see that? I'm going to highlight again. Look at the beginning here. At the beginning, it is very close to vertical. Vertical is the kilometer axis here. And as we move across, it's getting less steep. Can everyone see that? Okay, so what does less steep mean now? So I'm going to ask you, are any of those cars accelerating? We were looking for a curve that got more steep. Did any of the curves get more steep? Okay, I see Thomas's reply. What's everybody else thinking? Are any of those curves getting more steep? Okay, so then none of the curves are accelerating because none of the curves were getting more steep. Are any of the curves getting less steep? If so, we have deceleration. So which cars would be decelerating? Anybody else want to type something? Perfect. So both pink and gray are decelerating. What's the green car doing then? What's green going to do? It's not accelerating, it's not decelerating. What's it doing? Okay, remember the green car, it has negative correlation, but that doesn't mean it's a decreasing rate of change. It's a straight line. What do straight lines mean with regard to rates of? Okay, I'm going to ask that again. What do straight lines mean with regard to rates of change? The curve has negative correlation. That tells you direction of travel. If I want to know whether we're accelerating, decelerating, or moving at a constant rate, I have to look at the shape. Anytime it's linear, it's a constant change. All right, so constant rate of change. Now let's see if we can get the direction of travel. Which car or cars are or is moving forward? Moving forward. To move forward, you have to have positive correlation. So look for the curve that has positive correlation. Which curve has positive correlation? That's the car moving. Anybody else want to type something? Car moving forward has positive correlation. Nobody else wants to try? Okay. Now, the cars moving backwards would have negative correlation. Which curves have negative correlation? Anybody else? So green has negative correlation, but so does. So everyone has listed green. Another one, green and pink. All right, so we're going to play this scenario just so you can see. So we had green and pink moving backwards, and we had gray moving forwards. Play it one more time. Deceleration, green is constant rate of change. Pink and gray were decelerating. Show that to you one more time. All right, what we're going to do now is outline an exit slip. So your exit slip would be to, can we see this graph that's there now? Breaking that into different pieces and highlighting the pieces that would be accelerating in one color, the pieces that would be a constant rate, so you're looking for the bits that would be straight lines, curves that are increasing and getting more vertical, highlight those pieces, that's acceleration. Where it gets less steep, that's deceleration. So you can work on this, you can do this at home, you can draw this curve and you can send it to us and we'll give you feedback on how well you understood these concepts. And then the other activity we have for consolidation is in the OneNote. So I'm just going to get Mr. Hanta to go to the OneNote. And he's just opening up the OneNote now, looking for consolidation. Okay, so again, if we just click on moving cars exit slip first. So if you get into the OneNote and you've forgotten that little bit, there's that one I just mentioned to you now, the moving car exit slip. You can send that to us. And the next one down below that is the Venn diagram. And you can see this in your personal workspace. So on this Venn diagram, the red circle has positive correlation and the blue circle are things that are decelerating. So you drag the images to where they go. Anything with positive correlation gets moved to the red circle. Anything that's an increasing rate of change gets moved to the blue circle. If you have both positive correlation and an increasing rate of change, then you would belong in the overlap. All right, does that make sense to everybody? Do you understand the two pieces you're to be working on for consolidation? Everybody else comfortable with those two pieces for consolidation? All right, so how about a big thank you to Mr. Hanta, who has been my right-hand man with technology here, helping me out these last 2 days. I could not have done this without his assistance. Just a shout out, thank you to Mr. G. Hanta for his assistance. All right, so hopefully you found this to be useful. We'll see if there are other lessons that might lend itself to this. If you have any questions about this, you can contact us. And thank you for taking part in our live lessons, and enjoy the rest of your day. Take care.
Multiple people are now